So far we've been seeing how to build the network, and we've been using sigmoid activations, which is that function that is good for simulating the idea of the neuron as having an all or nothing response to the inputs, but we still can have something for which we can compute the gradients, and so we can use backpropagation. But now we're going to see some problems that appear when we try to build deep neural networks. We're also going to see why we want to build deep neural networks. But then we have this problem, the vanishing gradients problem, which happens when we are trying to propagate the gradient of the loss function through many layers. So we're going to see how rectified linear units help solve this problem, and so then we're going to talk about what kind of activations we're going to use in different positions of the network, and in which situations we're going to use those activations. Also related to the activations that we use at the end of the network are the loss functions that we need to optimize. So this lecture will be about how to match the problem with the activation at the output of the network and the loss function to train the network. So there is this universal approximation theorem. It's proven that if we consider a finite region, a finite volume of our input space, so consider this a hypercube between 0 and 1 with n dimensions, then if there is a continuous function that has values inside that region, there is, no matter how small an epsilon, as long as it's greater than 0, there is a set of parameters and a number n constant that allows us to build this composition of functions here, which is a linear combination of these parameters multiplied by any point inside there, plus some bias. Then this function, which this is proven, for example, for the sigmoid function, and then multiplied by another weight, add all of this up, and we can approximate the continuous function, whatever that function is, below this error epsilon. So this means that if you have a neural network with a single hidden layer, so you have one output neuron and one hidden layer, these will be, the V's there would be the weights for the output neuron, the W's here would be the weights for the neurons in the hidden layer, and if the neurons in the hidden layer have a sigmoid activation, your neural network with one single hidden layer is a universal approximator. As long as you put enough neurons there, you can approximate arbitrarily any function within a finite region. Of course, since we are considering between 0 and 1, but you can always rescale the values, so this effectively applies to any finite region. So if one hidden layer is enough to have a universal approximation to any function, the question is, why do we need more than one hidden layer? Why are we stacking more layers? The idea here is that even though we could use one hidden layer, when we stack and create a composition of consecutive nonlinear transformations, we can get more oscillations of our function with fewer neurons. And the oscillations are important because they are related to the Vadnik-Chevron-English dimension, which we saw last semester, gives us a measure of the power of a classifier. So basically, if we have a hypothesis class, this is where we are going to select our discriminants, and we can say that it shatters a set S if it can correctly classify all the elements of S for independently of the labels we put them. So, for example, suppose that the set S is this set of 3 points, and our hypothesis class are all straight lines in the plane, and we can shatter this set of points because independently of how we combine the labels, blue and red, we can always find a straight line to separate them. If we had a set of 4 points, for example, we could not be able to do this because there would be always some combinations of labels that would not be able to be separated with a straight line. So this is the Vapnik-Chevernenkis dimension of a hypothesis class, or a model if we are representing that hypothesis class, for example, in the neural network. The VC dimension is the maximum size of a set that the model can shatter. So the advantage of using deeper networks is that we need fewer neurons to have a high oscillation, the necessary oscillation, to classify, to shatter some higher dimensional set. So basically, we can do more with fewer neurons if we have deeper networks than if we have just one single hidden layer. In addition, there is also this theorem here that tells us that we cannot rely on one single model to be better than all the others. So basically, the no-free lunch theorem is a theorem in optimization problems in general, and it means that any algorithm or model that works better than average for some particular examples, for those we can find other examples, other sets of examples for which this algorithm or model will perform worse than average. So basically, this is true when we consider all mathematically possible sets of examples. In real life, it's more limited. We don't have all the mathematically possible examples, but it's still, in general, the case that you cannot count on one model to be better than all the others. And if we have deeper networks, we have a lot greater flexibility of creating different models, which is something that we don't have much with one single hidden layer, where we can only change the number of neurons, but basically the model will always be the same. So, for different kinds of applications, we may have a situation where shallow models are better than deeper ones. For example, basic linear models, the simple ones here, are better at memorizing interactions between features and are easier to interpret because we can assign different weights to the different features and know their importance. For example, these kinds of things that you sometimes see on online shops, customers who purchase this also purchase something like that. This is easier to implement with linear models because we can look at the pairs of features and how they interact. However, the problem is that this only applies to exactly those features. So you can easily find if a person who bought some item bought exactly that other item, but it doesn't generalize to kinds of items. For example, you cannot simply with a linear model discover that some person, if a person buys this particular movie, they like terror movies or action movies or something like that. So that kind of generalization you cannot note, you cannot find with simple shallow models. With deep learning models, they are much better at generalizing, at grouping things that are similar and finding those similarities, but they are much harder to understand and to figure out what they're doing. So this is an example of images that can fool neural networks and sometimes humans too. But if there are confusions between the mop and the dog or the bagel and the dog, we cannot really tell which pixel is responsible for that or what features specifically are responsible for the confusion, because this is all at the level of larger patterns the network is identifying. So it's very hard to interpret what exactly is going wrong there for the network to make that confusion. So this is a problem with deep models. They are much harder to interpret. But on the other hand, they allow us greater flexibility to find these patterns in the data. So one example here is a paper where the authors did a combination with logistic regression, so a linear model using a large number of features, and then deep learning for embedding in the hidden layers the large dimensionality of the features. So basically creating this network that funnels everything into this output unit. So the idea is that they could combine the strong points of a wide linear model that could find easily correlations between the features, and these deeper models that created this embedding that found the proper distribution, the manifold of the data, and looks for parameters at this higher level. So the shallow model is best at memorizing the co-occurrences. For example, people buying fried chicken and chicken and waffles, but not chicken fried rice and things like that. But it cannot find meaningful categories there. Deep models can find these categories and then manage in the representation when they are projecting the feature space, which has the large high-dimensional vectors indicating which products the clients have bought, and they project that into a lower dimensional manifold. Then things like meals, for example, fried chicken and hamburger, can be placed close together relative to things like televisions or motorcycles or something like that that are very different. So these representations can allow us to find similar things, but they are not exactly the items that the people have bought together. So this was this was implemented on Google Play. This is an example of big data processing here, because we have at the time 1 million apps being sold, about 1 billion active users, and they used a random set of 1% of customers. So basically, this is one of the ways these things are tried in these real systems. You have some trial run that is applying the new technique to a small sample of the customers, and then you compare to see if things go well or not. And they had about a 3.9% acquisition rate, improvement in the acquisition rate when combining these two models. So this may not seem much, but when you're dealing with these volumes of sales and so on, this is a lot of money. So this was an example of success. And this is just to show you that it's not necessarily the case that it's always better to go for one method or the other. In this particular case, they glued the two together and used them both to improve the results. So basically, in some cases, we can it's best to use those wide and shallow models. In other cases, deep models help us generalize better from those many features, or for space, an input space that has a very high dimension. And they're especially good with unstructured data. So that's why we're focusing on them here on this course. But this is just to give you this important idea that it's not necessarily the case that only using deep models is always better. There are situations where you have to experiment with other combinations. So now let's see one problem that arises when we use deep neural networks. Remember, we saw the backpropagation algorithm. We are activating all the neurons of the network as we pass from the input to the output. But then we need to find the gradient of the loss function with respect to each weight there on the network, so that we know how to update those weights. And to do that, we train all the derivatives. For example, in the output, we have the loss function here. We compute the derivative of the loss function with respect to the activation of the output neurons, and then the derivative of that with respect to the weighted sum of the inputs of the neuron using their weights, and then the derivative of that through the input of the output of the previous neuron, which is the activation of the previous neuron, and so on until we reach each particular weight that we want. This can be done tens, dozens of times, hundreds of times along the network, depending on how deep the network is. So since we are multiplying all of these derivatives, if one of them approaches zero, then everything turns to zero here, and we have no information on how to update this particular parameter. So as we go deeper in the network, if we use functions like the sigmoid activation function, which looks like this, and can easily saturate here on the negative or positive side, and the gradient, the derivative approaches zero, then if one of these layers has something with a derivative close to zero, everything gets turned off, so to speak, all the information about the gradient, and we cannot update the weights. And you can see this if you try using TensorFlow Playground. So this is a simple example of a data set that has this distribution. We can create a network with a single layer with a sigmoid activation that we choose there. And after about 400 efforts, we have a good result in classifying this data. If we choose something a bit more complex, these spirals, then one hidden layer with only 8 neurons doesn't work. In theory, there is a number of neurons that could make this work because of the universal approximation theorem, but we may need a large number of neurons. So one thing we can do is to add layers here, and that would be a more practical way of increasing the classification power. But even after, say, 1500 epochs almost, with the sigmoid activation, we are still not able to learn a good classification of this data. And adding hidden layers doesn't seem to work. Not learning, the network doesn't learn even though we wait many epochs. So the problem is this: the sigmoid activation is reaching zero at some point, or reaching the saturation point there. The gradient is close to zero, and we lose information about how to update the weights. So this is something that we can solve with the rectified linear unit. This appeared about 2012 because it's a very unintuitive way of solving this problem of modeling a neuron. We have remember that we have this biological neuron that we're trying to model, and the biological neuron has an all or nothing response. If the stimulus is not enough to fire the neuron, it doesn't do anything. If the stimulus is enough, then it fires. But this step function is not useful for backpropagation because we have a discontinuity on the function and we cannot use the derivative to update the weights. So the sigmoid activation function seemed an elegant solution to this because it looks like the step, but it's smooth and we can compute gradients. Other functions that were used classical was this hyperbolic tangent, which is similar to the sigmoid, but it goes from -1 to 1 instead of 0 to 1, but it has the same kind of shape. And this was very elegant, but all of these have this vanishing gradients problem. The rectified linear unit function is ugly and it doesn't seem very intuitive because it's basically if the input is below 0, then the output is 0. If the input is greater than 0, then the output is the input. So we have an elbow here with two straight lines. But the thing is that the elbow is enough to give us a nonlinear transformation. If it was a single straight line, it wouldn't work because we would be composing linear transformations. But with the elbow, it's nonlinear, and now it works for the network. And with this configuration, whenever the neuron is active, the gradient is always 1. It doesn't vanish to 0. So it allows us to propagate the gradient of the loss function even through deep networks without having the vanishing gradients problem. So if you try this was the one that wasn't working with the sigmoid activation even after nearly 1500 epochs. If we change this to a rectified linear unit, we don't need 300 epochs, so below 300 epochs we already have the result there. Because we are not losing information on the gradient, we can update the weights in all these iterations, and quickly the network learns what we want. We don't have a very smooth frontier here, so you see all of these jagged edges because of the way the rectified linear unit responds, but it can solve the problem that we want to solve. And we can even increase the number of layers and it still trains quickly. So this is after 215 epochs and the result is there. So rectified linear unit is a lot better than sigmoid or hyperbolic tangent activation for hidden layers, and this is the standard for hidden layers. There are some disadvantages that we will see that we can fix, but the main advantage is, aside from being fast to compute, it does not saturate, so if the neuron is firing, the gradient is never zero, it's always one, and it always allows us to bring information from the loss function to whatever weights we are updating. A disadvantage is that since the rectified linear unit has a gradient of zero when it's not firing, if it happens that it has a combination of weights that it never fires for all the examples in the training set, then it dies. It will never change those weights because the gradient will always be zero, so we have a dead neuron there. There are variants that fix this problem. So the problem occurs if the weights of the neuron make it be in this region for all the examples in the training set. So if this happens, the gradient will always be zero for that neuron and the weights will never change, so it will be stuck there forever until we finish training. And this is a dead neuron that will not be useful. We can solve this, for example, with leaky rectified linear units, where we don't have a slope of zero here, but a slight inclination, and basically this is a fraction of x on the negative part. In TensorFlow, it's like this, it's multiplied, not divided, so in TensorFlow it will be something like 0.1, 0.2, a value like that. And this gives us the non-linearity of the transformation. It has the advantage of not vanishing the gradient, and it doesn't die because there is always some gradient left there. So this actually works better than the standard rectified linear unit. There are other variants. For example, the parametric ReLU is similar to the leaky one, but the value there is also a parameter that is being learned during training, so it's an additional parameter that will be adjusted. The randomized leaky ReLU uses this value drawn at random from a uniform distribution between a minimum and a maximum. During training, it's random. After training, it is set to the average of the two extremes, but otherwise it works similarly. And then there are other variants like this concatenated rectified linear unit, the exponential linear unit, which combines this exponential function to the linear here. But basically, these don't seem to add much. And if you look at empirical comparisons between these approaches, leaky rectified linear units seem to be generally the best, or just plain rectified linear units. So these are the standard in hidden layers. If you're building a deep neural network, use ReLU or leaky ReLU for the hidden layers. That should be the best option. Okay, but this is for the hidden layers. Hidden layers are just doing these nonlinear transformations, and we don't want them to have gradients that saturate, because we are multiplying lots of those derivatives, and if they approach zero, things stop. And also they should be fast to compute, because we have to do them a lot during the training and the application of the network. So basically, leaky rectified linear units, or rectified linear units in general, are the recommended choice for hidden layers, with some specific exceptions like long short-term memory networks that are recurrent networks that use specific activations on some parts of the module of the network. But this is something that you're probably going to see on the second part of the semester on when applying in practice to the problems that you're going to look into. But this is, apart from these exceptions, the general recipe is to use rectified linear units in the hidden layers. But now it's different for the output layer, because the choice will depend on what you want to use your network for. So if you have a regression problem, generally at the output of the network, you don't want to constrain the values to some interval. If you use, for example, sigmoid activation, you can only have values between 0 and 1, which often for a regression problem is not useful. Unless it's a very specific thing, like trying to predict the pixel values on an image or something like that. But for regression problems in general, you don't want an activation function because you don't want to constrain the output to a specific interval. So in that case, you don't use an activation function on the output of the network. For binary classification, sigmoid activation is a good choice because it gives us a value between 0 and 1, which we can interpret as the probability of belonging to class 1, for example, like in a logistic regression. So sigmoid activation is very good for binary classification. It's also good for multi-label classification. A multi-label classification problem is one in which each example can have multiple labels. So we want a network that has as the output a number of neurons equal to the number of potential labels, and each neuron can give us the probability that this label applies. So suppose that you present the network with pictures of buildings, and you want to know if there is a door visible, if there are windows, if it has a chimney or something like that. These are not mutually exclusive, so you need each one to give you a probability between 0 and 1. And in that case, you can use an output of sigmoid neurons, as many as you need, and train those with vectors of zeros and ones, depending on the labels that apply to each example in the training set. Another type of problem is multi-class classification. This is different from multi-label because in a multi-class classification problem, the classes are mutually exclusive. Each example belongs to one class and only one class. So in that case, what we want the output to be is a distribution of values that tells us the probability of belonging to each of the classes. But each of the values must be between 0 and 1 because they are probabilities. And the sum of the values must be 1 because they are mutually exclusive classes. So this is the softmax activation function, is the one that we have here, that can map from a vector of k values into a vector of k values between 0 and 1, such that the sum equals 1. So if you use this expression here, that will give you this property, and so you can interpret the output of the network as the distribution of probabilities of belonging to any of the classes. So these are 3 or 4 examples: regression, binary classification, multi-label classification, and multi-class classification, where you have different activation functions at the end of the network, so that you can interpret the results according to what you need for your problem. Now, the question is, what loss functions are we going to use? And this will bring us back to things we saw in the last semester, which is, what do we want to minimize? So suppose we have some simple example of a linear regression, where we have a set of features, we multiply each one by some parameter, and we obtain a prediction. And so, changing these parameters, we can obtain different lines, different combinations, linear combinations of the features. For example, here, let's say the feature is only this coordinate here, the x, and we want to predict the y. And the question is how we determine which is the best set of parameters. And we saw that a common answer to this is to maximize the likelihood. So basically, we can imagine that we from our model can compute the probability of the data having that particular configuration, that particular set of values. For example, suppose that we are predicting this y value, the vertical coordinate here, as a function of the x, the horizontal coordinate, plus some error that we assume to be normally distributed. So if we have the function x here, which is what we're trying to model, so we have some set of parameters that we are adjusting to determine how this line is placed, then we can compute the probability of the data by looking at where the data is placed with respect to the line, assuming that this error in the predicted variable is normally distributed. So this would be the idea here, that we can predict the combinations of x and y values. Actually, we can decompose this in the conditional probability of having that particular predicted value given the features multiplied by the marginal probability of the features. And this is important because this is what we can get from our model there. So this, the probability of the data, assuming the parameters of our model, is the likelihood of those parameters. And what we want to do in adjusting this is maximizing the likelihood. Note that the parameters are not a random variable, so we don't talk about the probability of the parameters being right. That would not make much sense in this concept of probability as something that as the average, the expected value over an infinite number of trials, so the frequentist interpretation of probability. We can talk about the data having probability because we assume that the data was randomly sampled from the universe, but the parameters, they're either right or wrong, so it's not about probability. They will not change as we roll the dice again and try and obtain new values. So this is the idea of likelihood. We maximize likelihood of our parameters by adjusting the parameters so that the probability our model is telling us the data has of having that particular configuration is as high as possible. So for linear regression, we have this probability here, but we can actually discard the marginal probability of the features of the data because these have no relevance for our parameters. In our parameters, we only use them to relate the predicted value to the features that we are observing. So only this conditional probability term here matters. And also we can take the logarithm because we're trying to maximize this, and the maximum is the same, will be the same set of parameters whether we consider the actual product or the logarithm. So this simplifies the computations because multiplying small values will often lead us to problems. And now we can replace here, so the conditional probability of having some specific predicted value given the features is given by this function that we are trying to learn with our parameters plus some normally distributed error, which is what we can put here. So we now replace here the normal distribution of the error, and simplifying this, we obtain this expression. So basically, what this means is that if we have a regression problem and we assume that the thing we're trying to predict, the value we're trying to predict, is affected by some randomly distributed error over some function that we're trying to approximate, then the maximum likelihood solution for the parameters of that function to train our model corresponds to minimizing the quadratic error. So the sum of the squares of the difference between the actual values that we have in our training set and the values that are being predicted by our model with those parameters. Okay, so this is what we get in regression problem, typically, when we're trying to predict those values, if we assume that the error only affects the value we are predicting and does not affect the features we are using. So remember that this is a consequence of this probabilistic model here, where we assume that there is some function of x that gives us y plus some error that is normally distributed. So the error is only affecting the variable we're trying to predict and not the features themselves. If you try to do this with errors on the features, you get a different result at the end. It's more complex, it can be done too, but usually in regression problems we assume that the error is all on the predicted value. Okay, so this for this kind of regression under this assumption. But what about the general application here? Well, okay, before that, we need this loss function now because now we're going to look at the gradients and minimize this loss function using backpropagation. So we roll down this surface, okay? So once we have the loss function, we can train the network. But before we can train the network, we need this loss function. And this loss function was for this particular case of a regression problem, but in general, what we always want to do is to maximize the likelihood. That is, we want to find the parameters for our model that make the data as it came out of the universe by random sampling as probable as possible. So the first thing we need is that we have this set of data, and we know it was drawn randomly from the population with some probability distribution. We don't know what that probability is, but that was the distribution with which we drew the data from the population. And now we have in our model a family of probability distributions that depend on the parameters. So this is an important thing, is as we change the parameters, we are changing the probability distribution. Our model is telling us the data has. Going back here to the linear regression problem, this would be the family of probability distributions, because the function we have there is what we're trying to approximate with our model, and then we have this probability, this normal distribution around those predicted values. But for the general case, what we have here is that our model, once we fix the parameters, can tell us the probability of the data being as it is. For example, if it's a logistic regression, it gives us the probabilities of belonging to the class 1 or class 0. If it's a multi-class classification, it should give the probability of each of the classes, and so forth. So the maximum likelihood estimator for these parameters is the one that will maximize the probability of the data according to what the model is telling us. This would be the maximum likelihood data. So we usually don't use the actual product of the probabilities for all the data points. We use the logarithms and the sum. And also, if we are summing the logarithm of the probability given by the model for each individual data point, we can also consider, instead of maximizing this, maximizing the expected value here, so the average over all the points. It will give us the same thing, so we can say this maximum likelihood approach is equivalent to this. We want to maximize the expected logarithm of the probability that our model is telling us for data that is drawn from the universe with this probability distribution that we have when we collect data. So basically we have two probability distributions here. One is the one that exists in real life, which is the one that we are using when we collect data and build our training set. And the other is the probability distribution the model is telling us when we fix the parameters of the model. We can change that one by changing the parameters of the model, and that's what we're trying to optimize here. So intuitively, we want the probability the model is telling us to be as close as possible to the actual probability distribution the data has in the universe. And this is basically the problem of learning here. Because if the model is telling us a higher probability for points that appear more often and the lower one for those that appear less often, this will be maximized. If it does the reverse, if it assigns a lower probability to points that appear often and a high probability to those that are very rare, this will be a lower value here. So we can also measure this by using, for example, the Kullback-Leibler divergence. This is a measure of the divergence between probability distributions. And we are basically trying to minimize the divergence between the probability distribution the universe has for the data when we are collecting our data, and whatever probability distribution our model is telling us when we adjust the parameters and fix the values of the parameters. So basically, this is the idea. We are taking data from the universe with some distribution, and we want to train our model to capture, to approximate as best as possible that particular distribution. We don't know that distribution, but we can, from our model, choose from a family of distributions by adjusting the parameters, and we're going to pick the one that is closest to what we are observing in reality. And since this divergence, we can consider that the probability of the data itself is a constant, is something that we are not adjusting by our model. We are only adjusting whatever our model is telling us. We can consider this to be the maximization of the probability here of the model, or we can look at this as a comparison between these different probability distributions. In any case, what this amounts to is to minimizing this Kullback-Leibler divergence ends up being minimizing this product with the logarithms, which is the cross-entropy function. And this is why you often see in the literature talking always about the cross-entropy. And you can see even in TensorFlow you have categorical cross-entropy, binary cross-entropy, and so on. Cross-entropy appears a lot there, but it's basically referring to this function here that is telling us the divergence between the two distributions. If you have two distributions that are very different, you have a high cross-entropy because they are unpredictable. It's hard to predict one based on the other. If they are very similar, you have a lower cross-entropy between them. So this is something that you're going to see in general appearing in the literature talking about the cross-entropy loss function, but it's not necessarily a specific function because now it depends on what the activations are and the assumptions of the model. So it's more of this general approach here. So when we're going to find a specific loss function for training the network, we have to consider what is exactly the probabilistic model that we are adjusting when adjusting the parameters. For example, for linear regression, we assumed that what we're trying to predict based on the features is affected by some normally distributed error, and basically it's a normal distribution around whatever the model is telling us. So using that and trying to minimize this cross-entropy between the probability distribution the model tells us and the probability distribution of the data, this will be equivalent to minimizing the quadratic error between the predictions and the data points that we have. So for this particular case, under these assumptions of this family of probability distributions, this is how we adjust the parameters. But if we have a different problem and a different activation and a different interpretation of what the network is telling us, exactly the same approach of minimizing the cross-entropy between the probability distribution the model is telling us and the data, the one that we got from the universe, will give us a different result. For example, suppose that we have a sigmoid output on the network, and we interpret that as the probability of belonging to class 1. In that case, we have this product here to compute the probability of the data, which will be, for those that belong to class 1, the probability of being in that class is what the model is telling us, so the output of the network. Those that are in class 0, what the model tells us is that the probability of being in class 0 is 1 minus what the network is telling us, because it's the other class. So if we take the logarithm of that and minimize that, we have this logistic loss function, which is what we use in training the logistic regression and also in training a binary classifier network that is giving us the probability of belonging to the class. Also, we use this if we want to train a multi-label classification network that is giving us the probability of each label, and the labels are not mutually exclusive. So the same approach of trying to select the parameters so that the probability distribution the model tells us is as close as possible to what the data, to how the data is distributed, will now give us a different loss function because we have a different output of the network and a different interpretation of what that means as a probability model. If we go for multi-class classification, then we use the softmax cross entropy. Again, it's the same general approach, but now we have a set of neurons. We apply the softmax function to get a probability distribution of belonging to a class, and since we are interpreting the network like that, then trying to approximate the probability distribution the network is telling us to the data will lead to minimizing the softmax cross entropy function, which is here. So what is the important thing in practice when you're going to train networks is to remember that you need to choose a loss function depending on how you're interpreting the output of the network and what the network is giving. So for regression, typically you're going to use a linear output and you're going to use mean squared error as a loss function because you are assuming that there is a normally distributed error between the prediction of the network and the target value. And so the maximum likelihood solution is minimizing the mean squared error. For binary classifications, you are interpreting the sigmoid activation of the network as the probability of belonging to class 1. So this leads us to the logistic loss function being the one that tells us the maximum likelihood solution, and that's the one we use for this or for multi-label classification. And for classifying in more than 2 classes, we use 1 neuron for each class as the output. We use the softmax activation to get the probability distribution of the classes, and this will be the loss function for that. So remember, don't cross the loss functions or don't mix them incorrectly, because then you may have suboptimal results on the network because you're not using the loss function that makes the probabilities as you are interpreting the model as close as possible to the actual distribution of the data. Okay, so to sum up this part, we saw the differences between using wide or deep models. Remember that in some cases it's better to use wide and shallow models than just going deep. And then we saw this problem of the vanishing gradients, which happens when we don't choose the right activations for the hidden layers. So basically, use rectified linear units. That would be the general approach on the hidden layers, and you should not have much of a problem here. For the output layers, this depends on the problem and how you want to interpret the output of the network. And this in turn will also affect the loss functions that you need to choose.